Oh, that's lecture 6. As I said, on a conceptual level, in our first 5 lectures, we covered the basics of diffraction theory. Now we know how to solve how to solve a problem of diffraction by a half plane, at least using 2 approaches, Sommerfeld integral and Wienerhoff method. But like the sad reality says that it's quite hard to extend these methods to more complicated problems. And sometimes it's unnecessary. So today we will get into approximate theories, but some of them can work quite well. And today we will study so-called parabolic equation of diffraction theory. So it's like one specific case of wave propagation. Parabolic. But still, it's a very powerful tool. You should be aware of it. But for some reason, not many like wave theorists in UK use it or aware of it. There are some, but there is, I think, some people in Oxford who use it, and some people from like Soviet background. But it's a nice idea, so I think you should know. And it's probably was created. It's hard to tell by whom, but we associate it with, I think it's V.A. Fock, great Soviet scientist who can be called one of the fathers of like mathematical physics in Moscow State University, my alma mater. So, okay, let's finish with the introduction. So we have a Green-Goltz equation. Let's consider a Green-Goltz equation. As usual, that's our starting point. I will now put this tilde, because from Green-Goltz equation, as you can guess, I spoiled it, we want to get to parabolic equation. And so I will be quite vague, but I say let's consider a wave beam. So we consider a 2D problem. We are not going into 3D today. Maybe I should do some with 3D in the future. So what do we have? I don't know. And so, for example, we have some narrow high frequency wave beam. Like probably this idea was developed in 2 contexts. One of the contexts is propagation of radio waves along the surface of the Earth. It was a big deal back in the day, just for radio communication. Another context is laser physics, where you have a narrow, like laser beam, or you have some focusing antenna, you focus there, and then you have some dispersion. And so I will start with I will try to be a bit more physical, at least for the next 5 minutes, before we will go into mathematical details. And I have 2 characteristic lengths, like whatever it means. So I think like the width of my beam is h, and the length of my beam is l. And I want the following condition to be true. So I want A to be much bigger than H, and both of them to be much bigger than K minus 1, which is the wavelength. And so it's, yeah, you can think about it as a laser beam. So I have a very high frequency phenomena, but also I have other way to put it, I have only paraxial waves. So how do you think this thing will evaluate? Not evaluate, evolve over time. So, like, a normal idea is to introduce some amplitude function and to write it down as like the following profile. And then this amplitude function propagates with the beam, but it's slightly dispersion, so it becomes like this. That's probably one type of behavior we expect. Makes sense? So how do we describe this behavior mathematically? It's quite simple. Formally then we use the following substitution. So we have kind of a carrier wave that propagates along x-axis, and then we have, this is theta, then we have an amplitude function. So I have a carrier wave, so almost everything propagates along x-axis, and then I have just some slowly varying amplitude function. That's just my ansatz, that's how I want to look for a solution. Theoretically, I can just substitute it and then solve the equation I obtain, and the solution will be that. Of course, I will make some approximations to make things nicer. And these parameters, they are introduced to estimate this function. So what I want to be true is that the following thing will hold. So as my wave beam propagates, it changes very, very slowly again along l-axis. So the only frequent change is just the wave carrier, and the amplitude itself varies very slowly. And the same is true for h, but the scale h is smaller than l. Okay, so let's substitute it into the equation. What will we get? So we will get a normal derivative on y because nothing changed. Then we will get a cross term on x. So, and we got rid of this term because when we differentiated this twice over x, we get a k squared, so this term died. So now I have my, so now I will do some, scale analysis. So this term behaves as h minus 2, this term behaves as k minus 1, and this term behaves as L minus 2. So definitely this is the smallest term, because this is like the largest term. So I say I avoid stating. That's nice. Also from my, so what I get, this should be a very familiar to you equation. It's a diffusion equation. And this equation makes perfect sense. So now we have only first order on x, second order on y, and if we had here like time, and here we still had some space variable, this would have been a diffusion equation, with this being a diffusion coefficient. Or like it can be, a temperature diffusion, whatever type of diffusion we want to study. And why it makes sense? Because we say we don't have any much of a wave phenomena, the only thing we have is a diffusion of the amplitude. So the amplitude diffuses. And that's a mathematical explanation. Probably the only thing I can add is from this estimates, this equation should work well when h is of order n over k. So these two terms are all the same order. So when you apply it, you just check that this estimate works for you. But to be honest, I need to say this equation works in so many cases, you'll be surprised to find. Okay. So what's next? Let's study it the same way we were studying Gumbel's equation. So I will try to repeat the main ideas just for different equations, and probably it will make you more comfortable with these ideas. Nothing much changes, just some algebra. So what is the main difference? The main difference is that this equation now only supports waves that propagate from left to right, because that's how I chose my ansatz. Then I got rid of the second order derivative, and now I have only one type of waves. So let's derive this wave. Of course, we can guess. So for our original normal plane wave, we have expression like this. Now, I say that since my propagation is almost paraxial, I expect that my angles of incidence will be much smaller than my angles of propagation, so this is propagation. And then I will get the form expect. So we have this bit and we have this bit. So what I claim here that this is a solution, an exact solution to the parabolic equation. And it's more or less clear. Let's substitute, then this thing will multiply by this thing, and here we have a square thing, and they will cancel each other. Check it yourself. But that's, I will call the incident wave for parabolic equation. And today I mostly will study the case theta is equal to 0. So the wave will be just 1. H is 0. Nice. What else should we do for this equation before we will start solving any problems? As we did in our first lecture, we can find the Green function. So let's solve this boundary condition. This is a Green function for this equation. And it's slightly, my statement is slightly different than Parabolic equation. But so what's the idea? This thing is kinda a starting condition. So why I stated here that I have a line, and if I know field on this line, since all waves propagate from left to right, I can describe a solution on the right. So that's why I set up just a single point which produces a delta function. A point source. So this is how point source works. And yeah, okay, and let's denote the solution as this. And similarly to Green equation, we seek the solution. We can solve this problem in many ways. And but our my ideology, Musongenfeld ideology, just says use a plane wave decomposition. So I introduced some additional constants. You may not care much about them, but it's I took this and that and changed that for some side. Now I say, okay, this thing again will satisfy equation by default. So what we need to find is this amplitude function. And we, of course, to find this amplitude function, we should substitute this equation into the boundary condition, which is particularly simple. So we will get, so substituting into boundary conditions, what will we have? We will have the following relation. Okay, so who will tell me what is A? Somebody need to tell me what is A. Any guesses? What is A? Okay. Do you know what is a Fourier transform of a delta function? So this thing, okay, we substituted. Now we have a Fourier transform. So we need to do an inverse Fourier transform to find A. What is the inverse Fourier transform of a delta function? You know, speak. But what is this? Yeah, it's a whole spectrum. But what does it mean to be a whole spectrum? I torture you for a bit. So what does it mean to be a whole spectrum? Formula. So nobody knows. India. What's your idea? What is A?
We've just taken inverse transform of the
Delta function.
Yeah.
What we will get when we take
an exponential, e to the kt or something, or an x.
I need to say I'm a bit surprised. And we forgot. So what is this? Yeah, it's 1 over 2. Because, the main property of delta function is just reduces the integral to nothing, to a single value, but this value is 1 over 2. Okay, I'm glad we figured it out. But so far, is it clear to you what's happening? So you following? Good. Okay. So we know our solution as Fourier or integral as a plane wave integral, but we can actually compute. And maybe some of you already see the result. But after with the recent event, I will do the computation. Okay. So, what do you think the idea how to compute this integral? You know, I want, if I make it a full square, this thing over size, then I will get a Poisson type integral. And then it will be a square of pi and some constants. So this bit and this part I will call tau, so that will be my numerator. Thus we have 1/2 pi and for this I use standard integral from, I would have said from some handbook, but what I usually do, I open Mathematica and say, and ask it to compute this thing to have all the constants right. And I will just give it to you. What do we have? Finally, we have a nice expression. Cool. And like, what should we notice? We should notice this is one step simpler than what we have for Greenwald's equation. Because for Greenwald's equation we have some contour or integral, a special function. Here we have an elementary function. So we should be able to get more analytical results for this equation. And also, since all waves propagate one way, when we know green reconstruction formula becomes very simple. And maybe if you ever studied or quantum mechanics, you've seen this function before, because also this, I don't have the parabolic equation, but parabolic equation can be rewritten as a Schrödinger type equation. And this thing is called in quantum mechanics propagator. And I will explain to you today why it's a propagator. And then you'll be able to say, you know, smart words. But it's quite nice. It's quite nice. So if we have a slightly more general problem, we have not delta function, but some distribution of the field on the boundary. Then, using, forgot how this property is called, but like I would have called it decomposition property of, or like a convolution property of delta function. We have this thing. This just by definition. Then we have the following formula. Good. So I will give you a picture, which is like, so you need to have some visual image about it. The image I have is like this, 2D. And of course, all the stuff will work in 3D actually similarly, quite similarly. So we have some distribution of the field here at 0 line. Then we can propagate our distribution of field to any line. Just by computing a convolution with Green's function. So the image I have is like this. We do one convolution and we propagate our field. So it's kind of, if we know field on one line, we know it everywhere. We consider our problem to be solved. Okay. So, what do you think I will be solving next? Any guesses? Half-plane problem. And the solution to half-plane problem in parabolic case is quite trivial, which is called. So let me make some drawings. Diffraction. But now, actually, the orientation of our half-plane matters. So I want to consider paraxial waves. and then I will actually solve two different problems. I will say that this half plane is perpendicular to the wave beam. So the problem I solve is like this. I have my half plane. I have wave field falling upon my half plane. So it's just U in is equal to 1, as I said earlier. And so and here I have a Dirichlet boundary condition. So here U is equal to 0. And I get a solution right away because I have my boundary data defined on a line. So I have my boundary data defined here with just 1, and I have boundary data defined here with 0. And I say, amazing, let's use propagator formula. So I get, for some distant, the way I wrote it, I took some distant point L, and I say at this point my field will be given by following integral. And that's the solution for the total field. Also nicely, I like here, as you can see, I don't care about radiation conditions. I don't mention them because they already defined all waves propagated one way. So that's not a problem at all. And there is something that can be said about mixture condition, but here it's kind of satisfied by default, which is, so things work slightly differently for parabolic equation. Oh, that's solution. And okay, let's make a short break, and then I will continue in 5 minutes.